So our next speaker is Stephen Eglen. He's Professor of Computational Neuroscience in the Department of Applied Mathematics and Theoretical Physics. He's a Fellow of Magdalen College and also the Alan Turing Institute. I like an awful lot about Stephen's research, but one thing in particular was I read a talk from a few years ago, and he was talking about how to be an open scientist. There was a number of different steps that he recommended. One of those was go and talk to your librarian. And I've found that to be very sound advice. I work very closely with our librarians here, and they're very much leading some of our initiatives, especially around data carpentries and those sorts of things. And DSI sort of bringing them aboard as well. So a very big fan of your advice around that. So thank you very much for your talk, Stephen.
Okay, well, thank you very much for the invitation. It's very nice to be here virtually. So this talk follows on quite nicely, I think, from the last two talks in different ways. It gives some meat on sort of one area that we're pursuing at Cambridge, this project I'm going to talk about, and from the preceding talk with Ben about the levels of reproducibility. So CoCheck is what I'm going to talk about. This is joint work with my colleague Daniel Nist from the University of Munster. And right from the start, I am an open scientist, and so I like to drink my own champagne, as it were. These slides you can find actually on the web. You're looking at them now through a web browser. So you can go and grab them, and any links, you'll see that there's some links in there, so you can follow up with some of the key papers. So don't rush to write things down. Just grab the slides after the talk, or follow along as I'm talking. And hopefully the link will go in the chat, so you can get the link straight there. So I'm going to go into some of the details of CoCheck. I'll just start with some acknowledgements and declarations. So I'm on a couple of editorial boards, including bioRxiv and Gigabyte. You can find the details of this in a paper we published just last year in F1000. This work was funded by a combination of support from the UK Software Sustainability Institute and the Mozilla Mini Science Foundation. And a lot of this work has been in discussion with editors at various journals, including GigaScience, eLife, and Scientific Data. So I thought I'd try something new and try and summarize my talk in one slide right at the start. So if you've got the patience for a few minutes, it's just to hang on with this slide, and then this will sort of segue into the rest of the talk. So what is CoCheck? Well, what we do is that we, co-checkers like myself, will take your paper, code, and data sets. We run the code that you've provided on the data that you've provided. If our results match your results, we go to step 5, which you'll see in a minute. So that's success. If there isn't success and we find a discrepancy, what we do is we talk to you as the author to find out where your code broke. We don't try and fix your code. If you fix your code or data, we will go back to step 2 and try again to run your code on your data. And hopefully, through this process, we converge and we can get to the situation that not only can you run your code and get particular results, that we, as in some independent person, can do the same thing. This is what we call a very low level of reproducibility. I think it would sort of fall somewhere between levels 3 and levels what the heck in Ben's terminology. And we'll see how that follows out. So step 5, if things work correctly, is we write a report summarizing that we could reproduce your findings. And that's kind of like, you could imagine that's like a peer review report in the context of journals, but it's much broader than that. And then finally, what we do is we work with you to ensure that your paper code and data and our reproduction are all publicly available. So a key point of this is that once it's been reproduced, we want to be able to tell the world it's out there, it works, other people can go and take it. So that's effectively CoCheck in a nutshell. So now I want to rewind a bit and give you sort of the background context, some of which has already been covered in Ben's talk. So I sort of got this slide summarizing quite nicely sort of this is supposed to be deliberately supposed to be a messy, fuzzy cloud of all of the things that happen in your lab or in your group. You've got lots of data, you've got some code, you've got some statistical models, you've got some simulations, you've got results that have come out of those, you've got sort of lab notebooks that are trying to keep track of everything that you're doing. And unless you're super organized, this tends to be a big mess, right? And that's just the way it is. But somehow what we do during the scientific process is we take all of this sort of messy stuff and we try and boil it down into a coherent paper that we share with the outside world. So that's the dotted line. We export this shiny paper. And this is a, it's supposed to be a nice sharp object. It's nice and pristine. It's very sort of, clear and sort of optimistic about all of the findings that we have. And that's how we currently do science nowadays. Most of the time, the communication from one lab to the other is through this mechanism of the PDF. Now, mathematicians will realize that if you've got this, you can always generate this. This is sort of like a forward problem. Given this, all this data, theoretically, you should be able to, somebody else theoretically should be able to recreate the same results and write the same paper. However, nobody can solve the inverse problem. If I just take your paper from your lab, there's no way that I can go back and infer all of the mess that was on the left-hand side. And if you look what we're doing right now in sort of scientific communication is we tend to be using the paper as the way of sharing our results. And I think this is fundamentally misguided. And the sort of a lot of the open science movement is in recognition of this, is that we shouldn't be sharing the objects on the right. We should be sharing the objects on the left. And if we share the objects on the left, almost for free, we get the objects on the right. And you've already seen this quote earlier this morning from the first talk from Ben. This is viewed as the paper is just an advertisement for the scholarship, right? This is not really the scholarship. This is sort of the author's best spin on what they've done. This is actually where the scholarship really is. And this is what we should be sharing. So my personal sort of way into this came about 10 years ago, actually 11 years now. This article was published by Nick Barnes, who at the time was, I think, involved in sort of a UK-wide saga over climate, in fact, the ClimateGate saga at the UEA, University of East Anglia. He wrote this very provocative 2-page article. I highly recommend reading it. It's Publish Your Code, Computer Code. It is good enough. So there's lots of reasons that people say that they're not going to share their code. And I think they're excuses rather than reasons. And his view is that no matter what level, coming back to Ben's talk, level 1 being sort of gold standard, level 3 being okay, and level what the heck being not okay, whatever you provide is better than not providing it. The interested researcher will be able to go over it and make sense of it. So that's really my starting point. I really encourage people, if they haven't seen this, to read it. And so since then, we've seen a lot of approaches, from sort of informal approaches to sort of doing this like code buddies within groups, within labs or cross labs, sharing and trying to look at problems together. Within particular communities now, we see the notion of research compendia as a sort of complement to scientific articles, where there is more sort of documentation of the workflows in generating results. We've already heard about CodeOcean, probably the most successful platform for virtualizing research workflows so that others can run them again, and Nature. So this will take you to a Nature trial, which evaluated CodeOcean within the context of Nature journals. And there's even workflows now available for handling reproducibility with confidential data. For example, clinical data sets where the data isn't freely available. There's a system in France called Cascade where you can send your data off to this group. They get confidential access to the data. The code presumably is freely accessible. They run the code on the data and they write a similar report to say this is what they found. So there's lots of approaches. I think there's room for lots more. And our approach in CoCheck is to sort of point out that although systems like CodeOcean are great, and Ben was talking very nicely about virtualization, things like Docker, I think they're great, but they do set the bar very high They require a certain skill set to be able to generate these virtualization tools. Some things can't be virtualized very easily. For example, MATLAB is a product that doesn't sit in Docker containers very easily. But if you can get a Docker container, then it's freely available for everybody to use. And it's not quite forever, because Docker containers can't guarantee that, but they can sort of hopefully be reproducible over the scale of a few years. So CoCheck has gone in the opposite direction with respect to these two elements, who and for how long. So CoCheck simply says, was the code reproducible once for somebody else, right? That's all we're saying. Can somebody independent from the author who generated the code reproduce it at one point in time? So we take the code, we take the data, and we simply just compare the results that we get in a very loose fashion. So we're just saying, for example, are we getting the right kinds of outputs, not whether they're exactly the same. The contents of those files are not explicitly checked, because they would vary systematically from computational simulations, which are probabilistic. You'd always get variation. But they are available for anyone to view for themselves. We also deliberately do not ensure any validity of the code, right? Checking that a model is correct is a huge task, and anybody that says they can do that is obviously working either with very simple models or is missing how much effort is taking. Modern scientific models are so large and complex that it takes a huge amount of effort, often many years, to check the validity of the code. And I'll come back to that later. So this is the sort of typical workflow that we have devised with CoCheck. It's been running for a few years in the context with as a sort of an exercise in peer review. So we have an interested author, they submit their data and code together with their paper to a journal. The journal sends the paper out for peer review, and at the same time, they contact us. We'll do a code check. So a code checker is like a peer reviewer, runs the code, runs the data. Unlike scientific peer review, which is normally anonymous, this pathway between the code checker and the author is public. So there's a two-way communication to fix any errors, and we think that's productive. We don't need anonymity for that process. Once we get convergence and the code is working, we are able to then write certificates. We deposit our findings in places like Zenodo, and we return it to the publisher also, so that they can archive it together with the published paper. And so this is one particular instantiation of CoCheck that we've done. There are lots of alternatives of when to do CoCheck and so forth. So some of the dimensions. We have done it at all of these stages. It can be done before submission to a journal. It can be done after the paper has been published or during peer review. We try to work openly, unsurprisingly. So we try to do everything in public. So a lot of this lives on GitHub, for those of you who know it. We can do it as GitHub issues, so it can all be tracked. But in theory, it could all be done anonymously through sort of a third party. There's a choice of who does the code checking. Right now, it's a small group of us. We call ourselves sort of the code checkers, reproducibility reviewers, but it could be done in-house by editorial staff, or it could also be done by the scientific reviewer. Although I'm very keen to sort of recognize that scientific reviewers are already overloaded, and this is something that I think is distinct from sort of the scientific peer review process. Then finally, there's the issue of importance. Just because you've got a code check, what does that matter for your paper being published? Some journals may regard it as a strict prerequisite to peer review. eLife have informally told us that might be their view. It could be given as equal weight to peer review, scientific peer review, or, as is often the case, it's just seen as a nice extra thing to have. So we've got lots of particular ways to run a code check, depending on, for example, typically how the journal want to do it. We have various sort of 5 principles, though, that we try to uphold. which are enumerated here. We think code checkers should record problems, but not necessarily investigate or fix. It's not because we don't want to, but it's because, often code checkers are sort of very interested in these problems. We think that it's important for the authors to be involved in this, and often the authors can fix things a lot quicker than a code checker. We think that communication between the code checker and the author is critical, and having that done in the open, I think, helps. We are very keen to see that code checkers get credit for this through various mechanisms, such as through the journal acknowledgements or through citation of the CoCheck certificate. The workflows that we generate are auditable so that you can track them and see what was done in a CoCheck. And we firmly believe that everything should be open by default. So who's doing the work in this? Just to see that it's not, this is not an easy process. There is extra work required. The author has to provide the code and data, obviously, and some helpful instructions on how to run it. And that can vary from very helpful README to, well, you can kind of work it out yourself. Here's some MATLAB code. The code checker goes in, this is like the peer review process. We have to run the code. We have to make sure that we've got all the software installed to set up the environment and then write the certificate. And the publisher typically oversees this process and helps with depositing of the artifacts after code check. Who benefits? Well, we think very large communities actually benefit. The author gets a very early check that code works, which I think is vitally important. It's always a reassurance when somebody else can run your code. Code checkers enjoy this process because they get the insight into latest research and methods. It's a way to make discussions with authors, because remember, it's an open process. It's not like anonymous peer review. Publisher gets the benefits of knowing that the code and data are shared. We all know the cases of seeing data available on request. That can't happen here because we publish the data as a consequence of the code check. Peer reviewers are pleased by this process because they can see the certificate rather than having to worry about running the code themselves. And then, of course, the large fraction of readers in the world can, if they see the certificates, they know that they can build upon the work immediately, which I think is encouraging. So far, we've done this is the first collection. We've got about 40 code checks on the web so far. I wanted now just to sort of flick to, if I can, to a separate screen where I show you one of the certificates. It may not let me, right, that's better, sorry. I just switched to a browser tab. So this is what a typical certificate looks like. It has a sort of a standard template. It tells you what the original paper is. Now, if you look carefully, you can see that this isn't, I haven't picked this randomly. This is our code check of a technical report, actually, from Imperial College. This was the people in the UK will be very much aware of this. This is the famous Report 9 that Imperial College team led by Professor Neil Ferguson wrote on the impact of non-pharmaceutical interventions to reduce COVID-19. This model that he published in the report published in March 2020 was seen as instructive for the UK to introduce lockdown because of the predictions from the model that doing nothing would lead to 500,000 deaths within the UK. This model was highly contentious at the time. It wasn't available, the data wasn't available to run it. So several things happened very quickly. Microsoft and GitHub helped the team clean up their code base. For one thing, it was a sort of a typical complex model that had evolved over 20 years. So it was cleaned up so that it could sort of work portably and reproducibly. I was approached by an editor at Nature to do the replication to check that the code actually worked. And so I worked with the Imperial team. One of the other complications was that the data sets that you need to run these models were not available. So we had the discussion about making sure that the data sets as well as the code would be available. The good news for the Imperial team was that we were able within 2 or 3% to get the same results as they found. So these are our independent reproductions of their findings. I just want to come up to one table. The key table that most people in the UK were concerned about was this first column here. What happens if we do nothing? These are the total number of deaths for various estimates of the R0, the reproduction ratio of COVID. So we were able to reproduce this model. We published our findings, and Nature ran a piece on it, and it led to quite a lot of further work about this model, looking at, for example, which of the parameters were important in this. So that was our key success, and I think it was summarized quite nicely by this quote, "It ain't pretty, but it works." So from Hilda Bastian, the code is messy, it is complex, it's like most people's simulations, it hasn't been written to be shared before the fact. It's hard for others to run, but when you can run it, it is reproducible. So the results are reproducible in our hands. It doesn't say that the model is correct, nor can it, right? We didn't have the time to go through the many thousands of lines of code to check the model, nor even if we could check it, we could say anything about the knowledge then of COVID, let alone today. So this doesn't say that it's correct, it just says that the findings are reproducible. So just wrapping up, I've just got 2 more slides. Where are the limitations in this system? Code checking is like doing a peer review. Even if things go smoothly, it can take me a few days to get everything up and running and working and communication with the author. For early career researchers who are very keen on this, it's important that we give them credit. It's very easy to cheat this system, right? So somebody could cheat the system, for example, by sort of secretly encoding the results in their program, so that all the program does is spit out the files that we were expecting to see. My response is, who cares? The code is there, it has to be publicly available. So anybody who would try and cheat the system would immediately be seen to be a fraud. So that really is no problem. We want the code and data from the authors to be freely available. This can cause some problems with clinical data sets. We think this is a deliberately low threshold for gaining a certificate. As I was saying, with the COVID model, it doesn't guarantee that the code is right. It just says that it's reproducible. We had problems with the COVID model. It took a lot of high performance compute, and we were lucky to have the support of the Faculty of Mathematics high performance compute, and not only the compute resource, but the software, the support from the computing officers to actually to be able to set it up and run, which is often not included in these discussions. And we can't yet support all thinkable workflows and languages. We do rely mostly on open source frameworks like R and Python and so forth, although we're trying to expand that. So where does this go next? So we're talking with various journals, for example, GigaScience and Gigabyte, about embedding this into journal workflows, and Cambridge University Press are interested. We've got a huge body now of community of code checkers that we now need to train up to do this. We're obviously looking for funding to get a full-time CoCheck editor, which I'm sort of currently doing in my spare time. So if anybody is interested, this is an open source project. You click that link, it'll take you to GitHub, and you can come and get involved. And with that, I'll thank you very much for your time.
Thank you very much, Stephen. This is truly remarkable. I mean, I knew that model, for instance, that you mentioned. I knew it wasn't reproducible, and I didn't realize that you'd actually gone through and fixed it up. That's absolutely completely remarkable. So thank you very much. Ben, then Michael, then Nick, then Robert. Ben.
Thank you very much, Stephen. It's really fascinating, and I really like the kind of low-level approach. Like, it's going to raise awareness about the issue much more efficiently than and probably overcomplicated solution to this problem. So my question to you is, it seems to be applicable to any field using code, right? But where have you had the most successes or applications so far?
Great question. So we started by going through, I'm a neuroscientist, so the very first few examples were in my field. Daniel is a geoinformatician. So he actually last year worked with a conference, and a lot of the conference, he offered for the conference to work with the conference to do a reproducibility track. So if you look at last year, a lot of last year's CoCheck certificates on our register, a lot of them are in geoinformatics resulting from running that. So a lot of the papers that were accepted at the conference were reproducible. We hit a lot of the we were up and running before COVID, but like everybody else, I was sitting at home March 2020 thinking I want to do something, and it was just one of those cases that an editor knew that Nature were interested in, put me in contact with the Nature editor. I didn't think the Imperial team would give us the data, but they were very, very keen to get this done. And on the back of that, we did several papers of COVID modeling sort of predictions from the summer. So that particularly summer 2020. So that's been a big hit. Our most recent CoCheck that I just did a couple of weeks ago was for UNESCO on educational predicting educational resources in Colombia. Completely different. So it does span all disciplines. The key thing is we'd like CoCheckers to do it in a field that they're interested in, because it's hard to do a CoCheck on a field that you know nothing about, because you take so many things for granted. But that aside, that's what. So a lot of the CoCheckers are in probably the life sciences, where I imagine we're going to get most traction first.
Thank you.
Mike.
Hi, Stephen. Thank you. This is so brilliant, and I really hope to see it spread in a more widespread way. I noticed there was, a big focus on journals and publishers and authors asking for CoChecks as part of pre-publication, post-publication peer review. I was wondering what you thought about institutions getting involved as a commissioner for CoChecks. As I'm sure many are aware here, DORA, the San Francisco Declaration of Research Assessment, has become more and more popular. People keep signing on to it. Organizations sign on, and then they say, we aren't going to use journal impact factor to evaluate people's papers anymore.
Okay.
And then they say, now what are we going to do instead, right? So I see David Mower has proposed that institutions, when they're reviewing people for promotion, they should look at whether people have reproducible code, and using CoCheck for something like that seems like a really good place to do it.
We are talking to a group in the Netherlands who want to do it as an institutional approach. So there will be a pilot. Watch this space for a pilot to be announced. I'm not sure if I can name the institution today, but there will be a pilot announced hopefully in the next few weeks. But yes, this can be done by anyone at any time. It's not just for journals.
Nick.
Yeah, fantastic, Stephen. Really, really interesting stuff. I also knew about the Imperial stuff without knowing that this had happened, so that's great. A lot of I'll be talking about some related things, but more in terms of precise testing with software tomorrow. There might be some overlap, and I'd certainly be interested to check out CoCheck and see whether we can contribute or anything. The question I had, I guess, was what is the kind of organizational stuff behind this? Is this, doesn't look like it's a for-profit, but is it a bunch of people trying to make science better? Is it a non-profit company? Is it, how's it all working?
It's until very recently it was just Daniel and myself. We've got if you go onto our GitHub page, you'll see there's now a collection of CoCheck volunteers. I would dearly like for the next step to get to hire a full-time CoCheck editor. And the problem with these things, I've talked to lots of journals, they're all very interested, they'll all want to volunteer a little bit of time, but it really needs one person to run this, right, as a full-time thing, right? This is not my full-time job, right? This is something I do.
Yeah, you're an academic. Sorry,
yeah, exactly. Yeah, you know, this is something I feel needs to be done. I would really like to see this getting taken seriously.
Yeah, it's really inspiring stuff. So happy
Thank you.
Robert?
I just want to echo the enthusiasm that everyone's expressing for this kind of effort. My background had included 25 years in the sort of regulatory submission to FDA and that sort of fun. So the idea of CoCheck sounds pretty familiar. I just wondered when you listed a few points that stated the kind of the approach you were taking, and it sounded very practical. And one of them was that, you know, if it says it's going to generate 7 outputs, we check that it generates 7 outputs. But in your example, you said to within a few percent. And I just wondered if you have, do you color code your grades somehow?
So well spotted. The technical definition of a CoCheck is that it will generate the same number of outputs, right? And if you say it's going to generate 7 PDFs and it generates 7 PDFs, we pass. If those 7 PDFs are completely different to what you published in your paper, you know, they're pictures of the moon and you're talking about, you know, biological cells, you would still, in theory, get a CoCheck. We would write it in our report and say, hey, there's an oddity here, but theoretically you would pass. And the authors obviously would want, it's in their interest to have something that looks as close as possible. And of course, we haven't had that. We went the extra mile with the CoCheck certificate for the COVID model because it was so contentious in the UK about this model. There was so much talk about this model being unreproducible and that the model not being trusted. And we took it from when it was actually used March 2020, it was a known fact that it would crash if you ran it under particular circumstances. So they fixed all those kinds of bugs. They made it parallelizable so that you could run multiple runs and get distributions of results rather than just one run, you know, one value for a particular prediction. So we did go the extra mile, right? We you know, that probably took 2 weeks full-time effort just on making sure that we were saying this was in, because that's the one certificate that's had so many eyeballs put on it. If you go on the Zenodo repository, you'll see that it's had thousands of people download and look at it, and that's not typical.
Yeah.
So yeah, we did go, just that was exception rather than the norm.
Okay, thank you.
Moni?
Yes, it was a nice presentation, Stephen. Actually, I had a question which was two-folded, but one is basically asked by Robert. So you have already answered it just before mine. So my second part of the question is that as it is applicable in many fields, like you can work on climate, you can work on medical science, health science, and other areas. So if there is an error not in the code, but not in the way of doing it, like the process or probably in the content. So sometimes you have the people who is checking it, he might have some, you know, the reviewer, when they review a paper, they give you some feedback, like, have you read this paper or have you checked these are the things. So you give suggestions to them regarding their content, their work. But when you're only checking code, like I'm a computer science background, so we know like there are model checking and different software code checking already there, which checks the logic, but which does not check whether it is the content wise, like it is giving you the right answer or not. It only checks whether it is giving the answer or not. Just like you said, right? It is producing 7 PDF. So if 7 PDF produces, then you check it right. But all the contents in the 7 PDF or the way it has been done in the process is right or wrong, that has not been verified, if I'm correct.
That's right. We've set the bar deliberately low here, right? Just to encourage people to take up this process and start to share things. The hope is that over time, and by time we're talking many years, if not probably decades, by which we can leverage things like the first iteration, the grant application we wrote was going to use Docker to do all this, and we thought everything should be virtualized, and we realized that, you know, many authors, that would eliminate many authors, because, you know, lots of people, you know, smart computer scientists included, still don't use Docker and find it a challenge to get started. So the more barriers you add, the harder it is to get these things taken off. And, you know, hats off to CoCheck, right? If you get a CoCheck container, sorry, a CodeOcean, if you get a CodeOcean capsule, that's great. It doesn't solve all problems, right? They can't run long computation jobs, whereas we were able to run these COVID models that, you know, took up the order of several days to run. That isn't feasible in CodeOcean. So I don't think it's a one size fits all. And I think the simpler we start, and then gradually as the fields get expert in this, and like in particular areas of computational biology and bioinformatics, there is that competence, so that there is an expectation that you do things in such a way that you can use other sort of provenance tracking tools and so forth to take advantage and try and work out what the best way is. But we're very much start simple and get people involved and then ramp it up over time.
And we've got one more minute. So final question, Shimon. Maybe they can't talk. So I think the question was something, can you elaborate a little bit on CodeOcean and financial fields? I'm not really quite sure.
I'm not sure about the financial fields bit, but CodeOcean is this setup. It's a tool for running effectively virtualization containers. So you as an author have to upload your code in a format that can be run within something like a Docker container. It then lives on this website, and then anyone visiting, for example, a particular Nature paper can go click on the link, and it will, through your web browser, it will start up this container so that you can interactively, through your web browser, interact with the code that's provided and hopefully reproduce the same results that are shown in their figures. So I think it's a great tool. As I say, it's obviously only really practical to do on small scale simulations and data analysis, because there's a model that you have to run on a compute somewhere, and you can't just leave it cooking for several days. It's so in terms of viability across fields, it's hard, and it also, again, it puts the onus on the author to make their code run in a particular container, which it's not difficult, right? But it is time consuming to set that up. But I think, as Ben has already enumerated, there are lots of benefits to doing that. If you do it early in the process, it's then ready to run forever. So I hope that describes at least the CodeOcean side.
Yeah, so thank you once again for the presentation, Stephen. It's just truly remarkable what you've managed to get going. So hopefully you managed to get some funding and make things work.
Thank you
very much.